many of people are taking this class? Okay, so how many are just auditing? Yeah, so 2 auditing. Okay. Yeah, so yeah, because we need to know, do we need to change the classroom again? If it's only this amount, then no. But I think we have like 25 people officially enrolled, or maybe that changed today. Let me check. That's a good question, because when I checked last night, it still says 25. I was pretty surprised. I don't know why that many people are officially logged on. Oh, and I think it's, yeah, so today is the first day that you're allowed to take off your mask, but you're also allowed to have the mask, so it's your choice. I need to take off for Face ID, but yeah, that's yeah. Officially, there are 25 people on the list. Maybe I think I should see if I can who is here, who is not, just to make sure. 沈立成，对不起，沈立远 ，not here, okay. 蔡瑞琪here. 陈思伟 not here. 严家乐 not here. 翁子川 oh, he's sick, okay. 赵博瑞 not here. 洪启超 nobody's here, what's wrong? 廖延修 潘嘉许 oh, okay. 终于到你 finally got one. 连正安 okay, thank you. 洪挺志朱恒云傅佩婷梁静伟青木美丽罗俊元吴天冷张庭宇严子斌柯怡安 Ooh, who's this guy here for? 森林环之喜 I don't know why. 高敬元 not here, okay. 黄凯进辜新豪林立恩何卓耀 Okay, anyway, so apparently quite a substantial amount of people are not here, but we'll see how many people show up for the quiz. Yeah, I think we still booked the bigger classroom, but I do prefer this bigger classroom. So we'll see. Okay, so I think all of you should know, because you guys are the right people, or the good students who show up at 9 o'clock, instead of the other people that I call names that did not show up. Yeah, so this class is structured so that we have weekly quizzes, and so on the video that you watch. And so today we're going to do quiz 2 at the second hour. But for the first hour, there will be the office hour, and so you should bring your questions to us. If you don't have questions, then the TA will try to review that part of the material.
We've received one problem, but I rather put that in the context. And yeah, where's here? Quiz 1. Anyone?
Oh, I should have just call names from here. Okay. 翁子川 yeah, so he's the 6th. 廖延倩，对不起，廖延修，严子斌，詹什么名？哦，
詹晴雨，詹婷，詹艺宁，詹艺宁，詹 I guess.
I think he dropped the call. 柯怡安 not here. 吴天冷 is here. 方群均谓I think you also know. 萧雨良真正燕良何卓耀严家乐赵国瑞张庭宇顾新豪傅佩田卢思雨朱桂宇严这个实在太容易共鸣。OK， 廉政安。
I think there's one question about density of Q. Any other? No? Yes, please. No. Any problem? No? No, no, no. Cool. I'm sorry. But the first question this class is about to construct. We don't need to worry about those technical things about constructing. I will not go to that one. So like, once you know like dedicating cause if that's okay for you. You don't need to construct like additivity, multiplicativity, field, distributive law, everything you can skip that. Alright, so like we're not gonna test you in quiz, in exam. That's just technical part, and that's not important in like economic sense. So, okay. So the first question is that, we need to construct R. Alright. In subjects like analysis, we consider something about like continuity. So we're thinking about numbers as some continuous thing. So we're imagining numbers as I'll do this. Equal, almost equal. Yep. As hold on. Something that say it's like number one. That's how we imagine numbers. But there's an issue when we deal with Q. So we know like this number is not in Q, that's fine. So it seems that there are gaps in Q. So you can imagine Q is some set on a line that's like everywhere, but there's some gap. Alright, this Q. There's some gap. Oh, we want to fill this gap. Alright, so our goal is to find a way to fill these gaps. Any question? No? So our first way to call it Dedekind cut. So let's consider intuition. If we cut a line into two parts, there will not be a That's the spirit of Dedekind cut. So we want to split the set into two parts in this way, right? We say, okay, this one is part A, this one is part B. And there must be a cut point here. So either A has a maximal element or B has a minimal element. Alright, so we're trying to say that a cut A, B is a pair of sets such that A and B are not empty, and A union B equals to R. And the second thing is, if there's an A such that A is equal to X, then X in A. So this part say A and B are not empty, and where their union is whole line. And this part say, okay, anything is less than some A, it should be into A. So that means that A should be looks like this. So start from anywhere, this part should be in A. This part should be in A. B is similar. So we're saying that given any B, we're implying this one should be in B. Anything B, this one should be in B. So B should be looks like this one. Okay? And so what did the Dedekind cut tell you? That or we should say axiom, right? Axiom for Dedekind cut. Is that exactly one of the following holds.
Wait, sorry, so if A is in wait, sorry, where's the so we have an if, right?
Yeah, if A blah 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 if and if and if. Yeah, R. So if it on Q, then it's similar.
Okay.
So you just change it to Q.
R. Can you use that?
You mean Q?
Wait, sorry, did you put the A and B in the wrong direction?
No, because if X is less than some A, then X is.
Oh, I see. So A is the.
Oh, I have to write it in this way. X less than some A, X larger than some B. That's a cut on R. And if you want a cut on Q, you just change it to Q. Nothing changed. When we're considering about cuts. But okay, I'll write it on R so that it wouldn't confuse you. Exactly one of the following codes. One is maximum A exists, and the second is minimum B exists. So
I think I'm still confused about the if. So is because usually if it's an if, then there should be a then. Right? So which one is the then? So if there exists A and then X. No. Okay. Yeah, because the statement could be just there exists an A such that A is the sort of the upper bound in A, and B to be the lower bound in B. But
no, because there.
I don't know why there should be an if.
You mean like? What do you mean? Like?
I mean because
So that's enough if you.
Yeah, because if you have an exist, that means there exists this A,
Yeah.
there exists this B, and
Yeah,
and
so that's
sufficient,
just
right?
grammatical property.
Okay.
Yeah.
Okay, I see.
You can
Okay,
do
so
it this way.
sorry,
No, that's fine.
that's why I'm confused. Yeah, I'm a grammar person.
Sorry. So good about grammar. Okay. And go back to Q.
Hi, sorry.
Hey.
I just want to make sure that do we actually can define cuts on R, because in routing or in the video we all define cuts as a set of rationals.
Yeah, just go back. There's a way to do it.
And also what do you mean
we can do it on R. You can imagine that we're doing the same thing to cut the line on R. And that's why the Q is different from R. That so like in Q we don't have this property. I think in the video they use pseudonyms to talk about the completeness of real numbers, but that's not like for me it's not that intuitive. So that we're thinking about, if we're thinking about some way to fill in those gaps, then it's for me like hard to think about the existence of a soup can ensure
I think
that
the
kind of
problem
thing.
they have is that because well, the whole point for this section is to construct R.
Yeah.
And then, but here you almost like you already assume there's an R.
Oh, I see. So as I said, I just skipped the way that we construct R. We're saying that what properties should R have, and along that way we're discussing this kind of thing. So we're skipping the technical part of constructing R. And when we're constructing R with Dedekind cuts, we're actually like doing Dedekind cuts as you said in Q, and to construct something like, okay, there's no oh, I know you're constrained. Let me think about it.
So I just want to make sure that the property of cut written in the routing book is not the same as
Yeah, it's
said
not the
right
same
here.
as mine.
Okay.
I think reading book in routing they use Q, and what they use Q is that they want to use the technique of Q to construct R.
Okay.
So they're thinking about like, what is a real number? Real number is a cut of Q.
Yeah.
And
So when you talk about cut right here, you are talking about a different thing.
I'm talking about the same concept, but different purpose.
Okay, I will accept it.
So what I'm talking about cutting here is just like a cut on the line. And when they talk about cut, it's like you're considering this Q. And why they do that? Because we don't have R now. But for now, I just assume that there's R. Alright, and we're talking about like some property R.
Yeah, you shouldn't confuse people.
Oh yeah, sorry. I don't want to go through the technical on R part. I'm sorry, that's my fault.
Yeah. But anyway, so the idea is that so in the textbook and in the video, so because the whole goal is to construct the real line, and so you start from the Q and say, okay, let's define data on Q, and then let's use this to define what is it, or what R means. But here in the review, we try to take so after you know this approach that, okay, so now suppose we already constructed the R, and so what is the property of R? And so here we assume that, yeah, the R is, the real number set is already known, and then we try to define dedicated cut on the R. But yeah, but if you use this way to define or to construct R, then of course you don't know you don't know R yet. So yeah.
Like constructing R is something we call that everyone should go through like once in their life, but only that once.
Yeah, but this is their first time. Right?
Yeah. You have gone through that when like doing videos. Okay, go back to Q. There is something you're familiar with. So a cut, we'll say like a bar. So we're considering something a column Q. So maybe you can thinking about like A equals to X in Q, X squared as equal to 2, and B equals to right. And consider this kind of cut on Q. And you might notice that's notice that in my fan so like A has no maximum and B has no minimum. So that's why we're thinking about like it's kind of gap. It's kind of some kind of gap.
Your A is not correct.
But A is not correct.
Yeah, A is not correct because you need to be doesn't equal to R.
So a cat on Q. A cat on Q.
Yeah, if you A union B is not equal to doesn't equal to Q.
Oh, I see. It's not a problem that is one, but the other problem. X larger than 0. X larger than 0. 0. Something like that. Yeah. All right. is that what you're concerning about? Cool. So we're saying that, okay, we find gaps. Okay? And the second approach, the second way to say that there's no gap is to say that, okay, there's something like suit or lowest upper bound. So it's like cuts, right? But it's like only one side. So we're saying that, okay, if there is something like this and go through this way, there may be some set like here, then it must touch some point here. If you go, if some like ends like go this way, must stuck here, and so that this point is the lowest of the bound. If there's no gap, if there's gaps, so like you're thinking about if we're doing this, and it will not never touch this point. Okay. So the intuition is like intuition. Intuition is like this. So there's something, go this way, and if there is some set here, let's like bump into it at some point. Okay, so we may like define what is suit. What is the lowest upper bound? We say R equals to suit A. The suit is the notation for lowest upper bound. If R is an upper bound, everything is lower or equal to R. So R is an upper bound. Second, if something that is lower than R, then what would it be? Like, it's not an upper bound, right? Because it's lowest upper bound. So anything like lower than the lowest upper bound should not be upper bound. So everything lower than upper bound, this should not be upper bound. What do you mean by it should not be upper bound? That there is some point that is larger than that one. So there is some point larger than that one. Alright, your definitions of suit. And we're saying this we say that it has a list upper bound property. So that we say a set S has least upper bound property if any non-empty sets that has an upper bound. Then sup as prom exists in S.
In the definition, the second statement, it should be R prime smaller than A.
Yep. So we're discussing about like this upper bound property as this way, in this way. So if there's any set that this one lies in S, and we know that there's upper bound, so that we can start from some point. And so S prime exists, which means that if go this way, we'll bump into the set at some point. Alright. So that would, this is so far, but. So, we know our S LUV property there's no gap, so there's LUV property. And the second thing is that Q doesn't have such again, like consider this set. Alright. Consider A. There is an upper bound, but there's no least upper bound in Q. Which means that this point is a gap. Any question? No. Why it goes through this way is because it's more intuitive to me. But why we go to this way is because that it is more convenient for us to operate something. That we're talking about some sets or.
Wait, so which way is more convenient?
I think there's always our problem.
These upper bound.
Yeah, it's
Okay.
more convenient. Well, why I was saying that it's more convenient is because that when we're doing things like analysis, we are usually controlling some sets. I want to have some bounds of sets. We want to know like where the set is, or how small can it be? How small can it be? Some question like that. And so you can see that the soup, the concept of soup is a way for us to control those sets, to make those sets well behaved. That okay, you cannot pass this one. That's a good estimation of the sets. So it's more convenient when we use that like more deeply. So we're talking about like how to calculate soup, something like that. Okay? But before that, before we go through those examples about like how to calculate soup, I would rather go through some properties of R. Right. The first one is like quite intuitive. And has no upper bound. So the proof can see that how we operate soup and this kind of thing. You use this technique like this often. So let's suppose n has an upper bound. Say A. No, that's not. Say R. So there, and now it's upper bound. So, sorry. Sorry, it should be upper bound. By of the property of R. Sup and exists. Let's say R. Let's just do it. Oh. Right. R is the least upper bound, which means that R minus 1 is not. R minus 1 is not an upper bound. N minus 1 is still a natural number, like larger than R. It's not this. Okay. So I think you use the same technique to prove the Archimedean property. That is, you should like go through this on video. So the proof is similar. Alright. That suppose the set suppose the property fails for some xy. So y is an upper bound of the set and x. So you know the numbers should exist. Let's say R again. Alright. So you know there exists an M. Right, I use N. There's I use N. Such that NX is larger or equal to r minus x. The r minus x is just not, it is not come from nowhere. What we want to do this is because that we want to show that there is mx larger than r. So we bring 1x here. That's why this r minus x comes from. Okay. So follow this, we know that m plus 1x larger, sorry, it should be larger than r. And that brings you to the contradiction. Any problem? No? Cool. And the third one. Everyone knows inf, right? The greatest lower bound is like the inverse of the opposite. Okay. So, what's the first step to prove this statement? It's clear that 0 is one of the lower bound. So, suppose if equals to some epsilon, right? So what do you mean? What you mean that this will brings you. Well, what do you think that one over n is not? Why do you think that way? Because you think n is so large, right? So we're using like n is so large to prove that is n has no upper bound. So after this, we're saying this one. So because of this, n has upper bound. Which leads to a contradiction. And because clearly this set has a lower bound 0. And we know that anything larger than 0 cannot be the lowest upper bound. So 0 is the lowest greatest upper bound. Greatest lower bound. Greatest lower bound, yeah. Okay. So you know like several examples. So you can do like some questions very quickly, like consider some example. Maybe like m minus m over m plus 1. So it'd be like What's soup? Easier question. What's it? What's the inf of this set? 1 over 2, 2 over 3, 3 over 4, blah, 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 and over n plus 1. What's the inf? Inf. The 1 over 2, and what is soup? 1. Alright, we can do this. And you need this property to do this. You can think about it that way. So you have a good control on what is the fraction, so that you can do all those things. Okay, fourth. So, the fourth has the density of Q. It should not be density, it should be denseness. It should be denseness. I'll follow the rooting version, although like I'm not like that kind of version. I think rootings are all rooting. So intuition is in this way, that we must we're doing n like here, right? So we're thinking about that if we're going to construct, so maybe intuition. So we're thinking about like constructing x and over n y. Then, sorry, I'm not so sure if there is an equal in the rooting version. Let me check. Is there an equal? No, there's no equal. Okay, so we're thinking about nx. We're plugging some n into some nx and ny. But there should be some n between these. What's the condition? That's the jump between nx and y should be sufficiently large. So we're thinking about that brings us to want these two larger than 1. Cool. Okay. that n 1 minus x is larger than 1. I should follow Luding calculation. Excuse me?
Yeah, I did hand you the paper version.
That's okay. Oh. Okay, so I know. Want to put, what we want to do here is that we're saying nx is here, right? And n minus 1 is somewhere here. There should be some n minus 1. There should be some n here. And there's ny here, but that's not. Right, that's what we want to do. So we're trying to find an m that's bigger than nx, but it's so close to nx. And how we do that is to find an n minus 1 that is so close to nx, and that might like do this kind of thing. It's just can mean nx. So that if it in the interval of n minus 1 m, then everything's okay. I'm not sure if that's clear, but that's how I think it is. So such that nx and sorry, it's not n. It should be say n. I know it's not n. It should be z. Right. It should be. Yeah, it should be z. It should be. It should be z. And 1 and 2. And why these exist is because n has no upper bound. And so z has no upper bound and lower bound. Right. N has no upper bound. So that z has no upper bound and lower bound. And so that there exists some m. Where this m is to approach the nx as near as possible, right? Because you have m1 and m2 here. You can move m2 this way. You can move m2 this way. We're trying soup, all right? Soup and is lower or equal to nx exists. I should. Oh, now you can say we should use k. All right. And call it n minus 1. So that n minus 1 is larger or equal to nx and here. All right. And we know this gap is 1. Okay? And ny is somewhere here. It's larger than 1. trying to say that you see this one, and ny is larger than nx plus 1, right? So it's larger or equal to n minus 1 plus 1 equals to n. Hence, n minus 1, sorry, hence nx and ny.
Yeah, this looks like magic.
Yeah, but that's not that magic. So the intuition is here. Alright? We want to put some n between nx and ny. Why we want to do that? Because we want to put some fraction into x and y. So that we larger those jump so that it can be put it into an integer. There's an integer there. And how we put that integer here is to see that why this one exists. It's because we want to construct this that is so near to nx, so that if this one plus 1, it jumps into here. But it's not too far away from nx, because this one is the nearest to nx, and plus 1 should be like near to nx from this direction. And because ny and x is so large, so that n is here. That's the whole intuition about the proof. I don't think I have time, but I'll go through one technique that might be useful for you. And little technique you can use, technique of math, is that if you want to prove I'll give you two techniques. The one is if you want to prove equal, try to think about this one and this one. Just do two sides, don't just do equal. That would be, like, life would be more easier if we separate equal to these two. That's one technique. The second technique is if you want to prove x is larger or equal to y, you can try to prove that for all x plus n minus n plus 1 is larger than y. So, why this one works is because that you can see y minus x is less than n minus 1 for all n. So you know y minus x is larger or equal to 0. So x is larger or equal to y. That's a useful technique. And really useful. So try to think about it. Okay, cool. Any question? No, then the quiz will start like 10 minutes.